This brief presentation shows an example calculation that is laid out in a clear and coherent way using SI units. So here's the example I'm going to use. The question relates to finding the maximum force or load that a column can withstand. So the question states we have a hollow cast iron tube that's to be used as a column member within a structure. The tube has an external diameter of 150 millimeters and a wall thickness of 15 millimeters. We're asked to calculate the maximum load or force that the column can withstand, if the compressive stress in the column is not to exceed 80 meganewtons per meter squared. So we're going to show how to present this calculation. So the first step in the process is to assimilate the given information from the question or any assumed information that the question might indicate. Now, as we're calculating stresses in members here, I'm going to use a sign convention, and I'm going to state that tensile forces or tensile stresses are positive. So reading the allowable compressive stress from the question, notice I'm using symbols here, lowercase sigma for compressive stress. The compressive stress is actually negative 80 times 10 to the 6 newtons per meter squared. So I'm using negative here because I have a compressive force. Notice also I've removed the prefix given in the question. The mega is now become times 10 to the 6. Also from the question, we're given the external diameter. I've labelled that as capital D here. In the question, it states 150 millimeters. I'm converting that into meters because the above compressive stress is stated in newtons per meter squared. So I will now convert all my dimensions into meters. So 150 millimeters is 0.15 meters. The tube wall thickness is also stated in the question above. I've denoted that as lowercase t, and again, I'm converting the 15 millimeters given in the question to meters. That's 0.015 meters. So I extracted the information from the question and I converted dimensions to meters as the stress is stated in meters. Notice on the right hand side here, I've sketched the problem, and I would encourage you to always endeavour to sketch a problem from the information given. I think it aids both the understanding while performing the calculations, but also it makes it easier to understand for other engineers when they review the calculations. And the question wants us to find the maximum compressive load that we can apply to this tube given the allowable compressive stress and also the geometry. So to find the maximum load, we're going to have to first of all calculate the area of the tube, and as shown in the sketch here, the area of the tube will be an annulus section. So the question has given us the outside diameter D, and we're also given the wall thickness, which of course is this dimension here, and of course this dimension here. So step 2, to calculate the internal diameter of the tube, lowercase d, the internal diameter will be the external diameter, capital D, minus twice the wall thickness, minus 2 times t. So that's what's shown here. The outside diameter is 0.15 meters, and we subtract from that 2 multiplied by the wall thickness of 0.015 meters. That evaluates to give us an inside diameter of 0.12 meters. So step 3, I can now calculate the cross-sectional area of the column, called that capital A here, and I'm using the standard formula for an annulus. The cross-sectional area is pi multiplied by, in brackets here, the outside diameter squared minus the inside diameter squared, all divided by 4. Standard formula for calculating area in terms of diameters. So again, I state the equation that I'm using, I insert the numerical values from above, and I calculate the cross-sectional area. Notice it's in terms of meters squared, of course. And finally, step 4, I can now calculate the maximum applied load, the Pmax as I've labelled it above in my diagram, shown here. And we note from previous work that direct stress, lowercase sigma, is the applied force divided by the cross-sectional area. So by transposing the above direct stress equation, the maximum load, P max, is equal to the allowable compressive stress, which is the negative 80 times 10 to the 6 newtons per meter squared, and that's multiplied by the area calculated above, which is 6362 times 10 to the negative 6. Evaluating the maximum compressive load that can be applied to the tube is negative 508,938 newtons, or the maximum load can be expressed as negative 508.9 using a prefix of kilonewtons. So what's outlined here is a typical question and how to present the appropriate calculations to solve the question. I would strongly encourage you to apply this approach to all the questions that you're asked to solve involving numerical solutions. Always aim for clear and coherent solutions to all your problems.